Okay, so we're going to talk more about when you have your data here, and if you draw the density, it's some sort of bell curve. We're going to look at different ways that you can measure how spread out the data are. The word we use for that is variable, which is different than your variable in algebra class. You're not going to solve for a variable. This is just saying is how much do they vary, how much do they change. So for example, a data set where there was low amounts of variability, they didn't change much, that means the data is all in this narrow region here, whereas a high variable would be ones where your data is like really spread out here. In fact, this is exactly what they're trying to do with the coronavirus right now. They're trying to flatten the curve so that instead of having a whole bunch of people that are getting infected like on the same day, they want to spread it out so that maybe the whole people will still get the same amount, but your days are going to be more spread out here. And that way, the variability on which day it happens is going to be really high for people. That makes it so the highest point is lower than before. So that way we don't overload our hospitals and things. So that's the whole point of this lockdown that we're dealing with right now, is trying to increase the variability on our data here for how often people are getting sick. But regardless, getting back to the actual slides here, there are three main ways that we measure how variable something is, how spread out the data is. The range is one we're going to hardly ever use. All it's saying is what is the highest value minus the lowest value. The interquartile range, that one's used quite a bit more often. Every box plot is going to have that. That is, your Q3 minus Q1. That is what defines the middle class, right? That's the middle class here. And finally, the standard deviation. This is the one that mathematically is the nicest to use. It makes things work out well, but it's the hardest to calculate. I don't think we're ever going to calculate this by hand. It's just a gigantic pain, but it is the most mathematically used one, I would say. So here we have some symbols that we're going to use. As I said before, on our graphs that are normal distribution, the two things we're going to care about are the mean and the standard deviation. And so we need to have a notation for that. The notation I showed you before was these Greek symbols here. However, we only use those symbols when we have population data. And when we only have sample data, we're going to use the regular letter S, or this X with a bar on top, which we call X bar. And that's when we talk about sample data. So what I mean here is that for the data for fall semester exams, where we have the population data, that's when we're going to use these two. And then when we talk about our class's data, it's a sample, and we're going to use those two. So it just depends on what type of data you're talking about, which one is the appropriate measure here. Okay, so once we've figured that out, we want to see how is it going to work when you want to simulate what exam scores are going to be. So the idea is we're going to take our data from last semester. We are going to look at all that data and summarize it. And we're going to use that summary and say, well, okay, let's suppose I want to randomly get a class, and I'm going to assume that they're the same as last semester. What type of data would I expect to see? What would be reasonable? For example, if everyone got an A this semester, that wouldn't really be reasonable because that would be very different than the previous semesters. Similarly, if everyone got an F, that wouldn't be reasonable to expect either because it's so much different. Now, it's entirely possible for everyone to get an A. That could happen. It's just we wouldn't be able to expect it based on what last semester happened. So the idea is we're going to try to see that if we look at last semester stuff, how can we simulate what we should have this semester? And then that's what we're going to do. So what we're going to do is we're going to use our guru. We're going to create a class of the same size as ours. And we are going to do that by randomly picking people from last semester. And then we are going to record what the average is for that simulated sample. And then we are going to compare that to what we got now in our actual class. And what we need to talk about now is when we're taking people from last semester, we need to know if it's going to be without replacement or with replacement. Now let me explain what that means. Let's suppose I have a jar. And in this jar, there's 3 balls. One is A, one is B, and one is C. And I randomly pick a ball out. Okay, let's suppose I picked the ball A. Well, if I pick the ball A out and I go to reach for a second ball, what's the probability that I get A again? Well, there was only one A ball and I already picked it. So what that means is I could not possibly get A again. So this is when we talk about without replacement. You take the ball out and you don't put it back. Whereas with replacement, that means that you have your jar with your A, B, and C, and you pick the A out, and then you put it back in, so you have A, B, C again, and then you pick out a second ball at that point in time, and if you do that, you could possibly get the A again. And so we want to talk about whether we want replacement or not replacement because it will change what can happen in our simulations. Thankfully, on our guru, there's going to be a little button there that says with replacement or without replacement. So here's a breakdown of what we're talking about here. So without replacement, when we're doing that is we're saying that each student in our data set is going to represent a unique person in the population. Once a student is selected, they cannot be picked again, and it's like drawing cards out of a deck. So that, again, once you pick one person out, they're gone from the sample. You can't actually reach them again. On the other hand, with replacement, this is when, instead of each person being an individual, each person represents a group of individuals that are all similar. For example, if we made our ball of A, B, and C there, the ball A might be all the people that got an A. And so when you take one out, maybe someone else did get an A. So you should put it back in there to account for the fact that there was others there and we kind of grouped them together. Once we pick one out, we put it back in to try to pick it again. And the similar situation here is rolling a dice or flipping a coin. If you flip a coin, you get a heads. When you flip it again, you could get heads again. And so that would be with replacement. Whereas if you're drawing, say, a card and you get ace of spades, well, you're never going to draw that again. It's done. In fact, that's how what's called counting cards works if you want to play blackjack, but for another day. So we're gonna take our data set that we have. We are gonna simulate a class of our size by randomly selecting students. And then we are going to repeat this over and over and over again until we get, say, 10,000 different simulated classes. And we're going to look at all the possible class averages that those 10,000 got. And then we're going to see what happens. And so when we have these 10,000 different samples, we have this idea of sampling variability. This is saying is, if you look at those 10,000 samples, are they like this to where everything is pretty much near the same value, or are they spread out to where you could have class averages that are really high and class averages that are really low? So we're trying to see how this works when I measure that. And the graphs that I drew here, these graphs here, we give them a name. Those are going to be called the sampling distribution. And as it says down here in the last bullet point, you can do the same thing, whether it's average or standard deviation or median or whatever thing it is you're interested in talking about. It's just the one that we're going to do most often is the mean. which is what is labeled here. So here's the quick overview of what we said. We're going to simulate one class. We're going to calculate the class average for that class. And then we're going to repeat that over and over and over again. Now, we had this slide previously. So I want to kind of remind you here is when we have a distribution of a single variable, that's when you are looking at each data point is the score for an individual student. And the point of doing all that is to estimate probability for a single student to get a certain score or in a range of scores. On the other hand, sampling distribution, each data point is not one person, it's one whole class. And what we're trying to do is we're trying to estimate what a whole class might do rather than what an individual might do. So if you were trying to predict what grade you were going to get, you would want to use this side of things. If you're trying to predict what's going to happen on a whole class average, we would use this side of things. So it really just depends on what your goal in doing your problem is. And I'll take a little break here. We'll come back to the next video.